Hello, my name is Heather Jamieson. I'm really pleased to have an opportunity to share these research results at the 2020 Geoscience Symposium. Now, I have many co-authors and they all contributed, but I'd like to particularly acknowledge the senior author, Mike Palmer, who led this combined effort to determine the geochemical background of arsenic in soil in the Yellowknife area. I'd also like to point out the contributions of Kirsten Maitland and John Oliver, former MSc students under my supervision at Queen's University, and they collected and analyzed the soil samples that we'll discuss. So estimating geochemical background is important for both mineral exploration and environmental remediation. Identification of anomalously high concentrations that can indicate mineralization or areas of pollution. But this is complicated by natural variability in the concentration of metals or metalloids in soil, as well as anthropogenic activities. In the Yellowknife area, the complications include variable bedrock lithology, gold mineralization that's known to be associated with arsenic, and more than 60 years of aerially dispersed roaster stack emissions that has been documented in several studies. Bearing these factors in mind, our objective in this study was to identify the geochemical background concentration range for arsenic in soils in the Yellowknife area, and we're using multiple methods that would overcome the problems that are associated with these complications. The methods we used included mineralogical characterization, which we used to distinguish natural from roaster-derived forms of arsenic in soils. We used scanning electron microscopy to do this. We also used geospatial methods where we examined the distribution of arsenic concentration throughout the Slave geological province using multiple data sets, and statistical methods where we applied accepted techniques to calculate upper threshold and ranges of background arsenic concentrations. Now this presentation is going to focus on the first two. The details of our statistical approach are included in a paper that was recently submitted for publication. This figure shows a concentration of arsenic in the public health layer, which is the top 5 centimeters, of approximately 400 soil samples taken from undisturbed areas in around Yellowknife. Now this data set does not include any samples from the Giant Mine property. The highest values are just west of the former Giant Mine roaster, which is consistent with the prevailing wind direction, generally from the east to the west. And the concentrations drop off quickly with distance from the mine and from the city. Notice that the median value is 120 milligrams per kilogram of arsenic. This figure shows the same data, but in this case we've plotted the log of arsenic concentration with distance from the former roaster. Again, you can see the rapid decrease with distance, irrespective of the underlying bedrock lithology, which suggests that the variability is related to the former anthropogenic activities rather than natural geological influence. Within 20 kilometers of Yellowknife, 95% of these public health layer samples exceed the lighter dashed line, which is a federal CCME guideline for residential soils. That's 12 milligrams per kilogram. But beyond 20 kilometers, only 49% of the soils exceeded this value. Beyond 17.5 kilometers, no samples exceeded the Yellowknife specific guideline for residential soils, which is 160 milligrams per kilogram. This suggests that within about 20 kilometers of the former roaster, the soils are influenced dominantly by former mining and ore processing activities. Here's a similar figure that's plotted for deeper soils to test the possibility that only the near surface material was affected by former stack emissions. Although the fit is not quite as good, there's a similar pattern of a rapid decrease in concentration with distance from the former roaster, and there's no clear relationship with bedrock lithology. We examined 85 of the public health layer soil samples, the 400, using scanning electron microscopy. And we detected the presence of arsenic trioxide in 82% of those samples. This confirms the influence of roaster stack emissions because arsenic trioxide is not expected to form naturally in these soil environments. Moreover, it's been documented that 20,000 tons of arsenic were released to the surrounding region in the early years of roaster operation. The image on the right shows one of the particles of arsenic trioxide. They're rare, but they're easily identifiable. Arsenic trioxide was detected in all 50 samples except one, where the total arsenic was above the Yellowknife specific remediation guideline of 160 milligrams per kilogram. Now, the mineralogical characterization technique that we use allows us to make these mineral maps, and they assign different colors to each mineral phase. Most of the soil samples consist of quartz and feldspar. Some cases is organic material. It doesn't really show up on these images. In this example, we've enlarged two areas where particles of arsenic trioxide have been identified. Now, in all the samples, we saw some other arsenic minerals. The arsenic trioxide, As2O3, is coming from the stack emissions. We see arsenic-bearing iron oxide, and that could be natural or it could be from the stack emissions. It's known that the roaster produced some arsenic-bearing iron oxides. It's quite difficult to tell the difference between the two. Sometimes we see scorodite, an iron arsenic mineral, and we see that in samples near the Con mine. And that makes sense because in the later years of operation, they used an ore processing technique that produced scorodite as a waste product. Arsenopyrite is what we would expect to see as a natural arsenic mineral, but in fact, it's very rare. This figure shows how much of the total arsenic in the 85 soil samples we examined can be attributed to roaster-generated arsenic trioxide. That's the phase that's anthropogenic in origin, and it's been added to the soils, we believe, by aerial deposition from former stack emissions. The black downward-facing triangles show the total arsenic concentration. You've seen that in the previous figure. The red upward-facing triangles show how much of that total arsenic is contained in those particles of arsenic trioxide. On average, within 15 kilometers of the former roaster, 70% of the arsenic is hosted in arsenic trioxide. So clearly these samples cannot be used to determine a natural geochemical background. Fortunately, we have a large database of 1,500 samples of arsenic in soils and tills that was produced by the Geological Survey of Canada, and it covers much of the Slave Province. We can use this to estimate natural geochemical background. As in the first figure, the approach here is a box and whiskers plot. But while the median value in the previous figure, which was for the public health layer soils near Yellowknife and was 120 milligrams per kilogram arsenic, the median here is 5 milligrams per kilogram. We can see areas of known gold mineralization, such as the Courageous Lake and the Indian Lake areas. These can be recognized. And our analysis shows that there's slightly higher upper thresholds for arsenic concentration in volcanic units associated with greenstone belts. So in conclusion, we can say that the soil samples taken in the Yellowknife area cannot be used to indicate natural geochemical background. The presence of arsenic trioxide, clearly from roaster stack emission, precludes that. However, based on a large number of samples taken by the Geological Survey of Canada in areas away from Yellowknife, we can say that the natural geochemical background can be estimated as a range between 0.25 and 14 milligrams per kilogram. Notice that this is much higher than the previous government estimates that were used to derive remediation guidelines, which for the Yellowknife area is 160 milligrams per kilogram. We'd also like to say that any determination of the risk associated with the arsenic-rich soils in the Yellowknife area requires further work beyond this kind of study, work on bioaccessibility and exposure assessment to determine any risk to human and ecological health. Thank you for listening. I'd like to acknowledge our financial and other supporters, Government Northwest Territories SIMP Program, NSERC, Gold Terra, and the Yellowknife Dene First Nation.